We are missing enough people that I've decided to record the answers to Worksheet 2 so that all those people who are out there wandering around the great wide world learning about whatever the heck they're learning about uh, can fall asleep watching this, can learn from this video on their own time. So if you guys will open to page 242 in your purple, what? 243? You lied to me, maroon sweatshirt. You said 243? Okay. Well, now that I've recorded this awkward conversation, I think I'm going to start again. So, I could keep. Should I roll on? All right. We voted, and we're going to keep going. So, now that everyone important is back and we're ready to get going, we're going to go over, I left this blank because we do have a test next class. When's the test? Next class, whatever that is. I know it's Monday right now, but in the future it might not be Monday. In the future, like next year, next class could be a Thursday, couldn't it? Right. So, we're going to go through all these little pieces here. The first couple questions all kind of revolve around an idea of that's called collision theory. And collision theory goes like this. You have some particles, like these red ones that are all identical in size and shape, and you have these blue ones, which are a different particle. In order for them to collide, to react, sorry, I skipped a word. In order for them to react, they must collide. So this particle hits that particle, and there might be a reaction. Cool? Or perhaps particle A hits the blue, or the red particle hits the blue one, and there might be a reaction. So let's answer this one thinking that through. Why does a decrease in temperature cause most reactions to slow down? I didn't hear anything they said, but I'm going to assume they said there's less energy, there's fewer collisions, there's less energy, and fewer collisions. And so if there's fewer collisions and with less energy, there's going to be less reactions. Why does a decrease in concentration cause a reaction to slow down? Let's decrease the concentration of the blue ones. Ooh. Now, with fewer particles, there's fewer collisions. This red guy has no one to slam into now, right? So again, if there's lower concentration, there's going to be fewer collisions per second. Fewer collisions means fewer reactions. Oh, that's a big sigh right in the microphone. Sorry, I just sighed. It's a good thing we don't have smell-o-vision. Why don't all collisions between reactants result in products? It's actually about energy also. Do you go here in classroom land? Do you remember what we call the energy that is like when things collide and they react? It has a name from the notes. I can't read lips, but it sounded like he was trying to say activation energy. Activation energy, or like most chemistry vocab words, is just take the thing and say it in reverse. It's the energy to activate a reaction, energy to get it started. Activation energy. If you don't have enough energy, they won't collide hard enough to break apart. The second thing, they must be facing the correct direction. Usually, the term that's used to imply the direction they're facing is orientation. So let's say that Black Jacket and I both had markers. Here you go, marker. Good catch. Perfect catch if you can't see at home. Now he and I both have markers. We're going to throw them at each other. And I want him to throw it so that the cap in my marker sticks into the base in his marker. It's possible. How likely is it? How many throws do you think it would take? Like probably a whole lot, right? for me to throw a marker and for it to stick in the bottom of his. Ready? Set. What? I'm, I'm trying to get my marker cap to stick in the bottom of you. Ready? Set. Go. What are you doing? Yeah, you've got to throw it. Okay, give it back. All right, ready? Go. Absolutely no chance with us doing it. You have to hit with enough energy. We didn't even hit. So we didn't collide. Is that an example of collision model on itself? The particles have to collide? Went in the trash? Goodbye. Okay. That one's inside a wrapper of something in the trash can. Glad I'm recording this. So, look, I have a whole box of more markers. The particles have to collide. What's the chance that they do collide and they collide on the side? Would they stick together if they collide on the side? No. They have to collide perfectly to stick. And, I don't know if you noticed, like, to put it in, there's some effort, isn't there? So they have to collide with enough energy, and they have to be facing the right direction. We probably would have had to throw hundreds of markers at each other, maybe thousands given that first throw, for the collision to result in what I was just describing. One reason I like that stupid example with the flying markers is that the particles are flying around and they have no guidance system. It's not like they're like, oh, look over there, there's a particle. I'm going to go that way. They collide completely by random, don't they? It's totally by chance. Okay, number 4, at equilibrium, the rate of the forward reaction and the rate of the reverse reaction are equal. I'm going to do a demonstration, but you can't see it at home, so I'm just going to pause. You guys have to wait. Yeah, you guys will remember that. You'll remember that demo forever. I mean, he'll never see right again. But so at equilibrium, it was a 3-to-1 ratio, and it was also a 6-to-2 ratio. Both of them had the same ratio. Yes. They both had the same ratio. Were they exchanging reactants and products at the same rate? Yes. The key here is that the rates are equal, not the quantities, how much they are exchanging. Quite often it's lopsided one side, where there's like a whole lot of products and very little reactants, or vice versa, in terms of how much you have, but not in terms of the rate. All right, in number 5, we're supposed to write the equilibrium constant expression. That is the K thing. K equals, what are the products here? First product is water squared times chlorine squared. Just going to drag that line out. And then the reactants were hydrochloric acid to the 4th times oxygen to the 1st. My first question for you all here in classroom land is, where did the 2, the 4, and the 1, the squared quad to the 4th powered, what is that, quadded? Thirded? To the 4th powered, they are the coefficients in front. Yeah, 2, missing 1, and a 4. So those exponents in front, those coefficients in front become exponents. The other thing that we need to fix, there's one thing wrong with that, is anytime we have a solid or a liquid, we replace solids and liquids with the number 1. Because they're not actually moving. They're not actually impacting the rate. They are waiting for the gas to hit them. Is there a liquid in this reaction, or is there a solid? There is? There is a liquid. Which liquid? H2O is currently a liquid. It's not a gas, and it's not solid. It's not ice or steam. So we're going to erase the H2O and replace it with a number 1. The gas, and here's the reason behind that, because this kind of irritates some people. The gas is flying really fast. Do you know how fast a gas particles fly in the air in this classroom? It's 200 meters per second. 200 meters per second. Or to put that in a different perspective, the like length of one side of the track is 100 meters, half a second. The length of the track and the time it takes you to go one, and the gas is to the other end. Which is why you don't have to worry about running out of air in your little bubble. I don't know if you've ever thought of this back there. Have you ever thought about the fact that I'm breathing in the oxygen or breathing out the oxygen? How is it I'm not using up all of the oxygen right here and passing out? Because it's moving so fast, what just left, maybe the guy in the maroon shirt's mouth, is flying around the room, and eventually it enters your mouth, right? All this gas in the air, you're all sharing it, which is a little bit creepy at the same time. Yeah, some of the particles you're breathing in right now used to be in somebody else. So it's also mathematically true, though, that some of the particles you're breathing right now used to be like in George Washington. Used to be in any historical figure at all. There's so many particles in your body that you're constantly exchanging them. So some of the atoms you're inhaling right now used to be in someone else famous, which is kind of cool. Or someone that's currently famous, but not that exciting. So, all right, let's go to this one here. If solids and liquids get replaced with the number 1, how does that expression get changed then? What do we put on top? 1, because that's a solid, right? Times, why is H2O being counted this time? It's a gas, right? It's flying around, and it's going to hit that solid, sound effects. It's going to hit that solid and react with it. And on the bottom, 1. Yeah. On the bottom, we also have a 1. Actually, before we get down to this number here, I want to just kind of do a quick little explanation of something you've probably seen before. Before that, here's a little sheet of paper. Do you agree that looks like a piece of paper? It's an amazing piece of paper. And this is an oxygen atom. Oxygen atom hits piece of paper, bounces off. Bounces off. And the room is filled with oxygen atoms, and they're all flying at like 200 meters per second. If you had pure oxygen, this could result in a fire very easily. Have you ever seen an oxygen tank? Maybe your grandparents maybe are on oxygen or something like that. Well, on the oxygen tank, it looks like a big propane bottle. There is a warning sticker with something that kind of looks like that. That's my attempt at making fire. No, not a hand. I guess I could put eyes on it. Looks like Wilson from what's that movie? Castaway, yeah. But oxygen tanks always have a big old fire symbol on it. It's not oxygen that's flammable. Oxygen makes other things flammable. It breaks them apart. So if you put this piece of paper in pure oxygen, the collisions would be enough to drive it to catch on fire. Because what's the reaction? It's paper plus oxygen produces fire, right? And carbon dioxide and water. Right now, is the room pure oxygen? No, it's only 22% oxygen. But if you kick it up a couple percentages, everything starts to become flammable. How about later on we make some pure oxygen and we show how it can light things on fire? All right, we'll do that in a little bit. All right, let's go back and knock these out. First of all, number 7, what would the expression be? We have acetic acid makes acetate and hydrogen. What goes on top? Acetate and hydrogen. And those values are supposed to be multiplied. Make sure, kind of want to emphasize that those are multiplied together, and then the acetic acid's on the bottom. So then someone did this experiment not once, not twice, but thrice. They did it 3 times. So let's plug in the data for experiment 1. So how are we doing that? We're just taking these 3 values, plugging them in, to the right spot, then grabbing a calculator and letting the calculator do the work. So the calculator spits out that number, 1.8 times 10 to the minus fifth. It's kind of a weird looking number, right? It's not something where you could look at these values and go, that looks like about 1.8 times 10 to the minus fifth. If you can do that in your head, that's very impressive, but not required. How do we do trial 2 then? Same thing. But here's where it gets a little weird. We plug in these numbers. Answer number 2 is also 1.8 times 10 to the minus fifth. And that's because K stands for constant in these systems. Yeah, I know. Spell it with a K. K for constant. So if K stands for constant, do you know the answer for number 3? Do you even have to plug it in? No. If it's 1.8 is the constant, then 1.8 is the constant. That's okay. It just records audio. It didn't see you drop all that stuff. Thankfully. Whether you plug the numbers in or not. That's one of the things that's nifty about nifty. I said nifty. One of the things that's fascinating about equilibrium is that once the reaction achieves equilibrium, you get the same ratio each time. I don't think anyone would have looked at these three and seen that they automatically equal the same value. You have to plug them into your calculator and carefully do the math. Ooh, that's a nice picture. All right, number 8. I think we're on the back now. Cool. So number 8, again, it's an equilibrium problem. I suggest you start off with the setup. When you set that up, you have hydrogen on the top and oxygen on the top and the water vapor on the bottom. What do these 2's mean for hydrogen and water vapor? But what's that going to mean we do to the value? If we plug a number in, it's going to be the second power, or squared, right? So then we have to throw the numbers in that we've been given. And what's weird about question 8 is we have the constant, we have the water, we have the hydrogen. We need to solve for the oxygen. And I think I worked this out last period, and my brain is telling me an answer. But I would really like someone to check this answer before I write it down. Because if I write it down and I'm wrong, that's going to be just embarrassing. All right, I think that's the answer. My batteries are low. That's a description of both my calculator and me. According to my students, I am correct. That is, the value for x is 0.080. All right, let's go on to number 9. Number 9. Here we have another reaction. We have chalk or limestone, sometimes called chalk, sometimes called limestone. Calcium carbonate solid, calcium oxide solid, makes carbon dioxide gas. There's a whole lot of solids. What do we do with solids and liquids? It's literally typed on here, but just in case you can't read, I'm going to shake this around. Now you really can't read. Anytime we see a solid or liquid, we replace it with the number 1. So this expression, while it starts off looking exciting like that, we replace 2 of the values with a 1, and suddenly it is very easy to calculate K. I can do that math in my head. Who can do that math in their head, even though it's scientific notation? Yeah, it's -3, just like in the question. Yeah. And so K equals 2.1 times 10 to the -3. This is the reaction of the decomposition of limestone or chalk. Depends on what you're working with. Now, it slowly becomes that. We're not talking about speed in this equilibrium expression. We're just talking about where it gets balanced. So if you sealed the container, That was me. I just hiccuped. I apologize. If you seal the container, it would make that much carbon dioxide, and then the reaction would be at equilibrium. It would appear to stop. All right, sliding down. Now it's time to get shifty. Predict the effect of decreasing the temperature. That's where decreasing the temperature. And I'm going to circle the heats so I know which side has the heat on it. And then we're going to do a demonstration about this in a little bit also in the back of the room. Those of you at home, if you're not. For those of us in class, we're just going to do this as a demonstration. It's pretty cool. So this reaction, if hydrogen and chlorine react, they will make hydrochloric acid and give off heat. True? If you remove the heat, this reaction can't go backwards. It can't go backwards. It needs the heat. Heat plus hydrochloric acid pushes it this way. If they decrease the temperature, the reaction will shift towards the right. What would happen in number 2 if they removed the heat? Move to the left. And C, I said number 2, I meant B. And C would also go to the left. Reaction B is probably one of the world's most famous reactions. It's the Harbour Process. It's how you take nitrogen and hydrogen out of the air and you make ammonia. And ammonia can be turned into a fertilizer and into explosives and all sorts of stuff. That was perfected in around 1908, 1910, something like that, by a gentleman named Fritz Haber. He won the Nobel Prize for that because 2/3 of the planet gets their food through that reaction now. So it's a rather important reaction. Okay, number 11, if the concentration of nitrogen is increased, that's on this side. I typically say, hey, think of it like a seesaw. If there's too much nitrogen, which way would this reaction shift? It would shift to the left to get rid of that extra nitrogen. The reaction shifts away from an addition and towards a subtraction. Number 12 is the most evil question on the entire homework. It actually is a little bit evil. So let's kind of underline what the question's about. An increase in pressure. I suggested when we did the notes that when the pressure's increasing, you flip it around and think about volume. It's a lot easier to imagine volume. And if you're going to imagine volumes and pressures, you focus on how many moles there are. And in this reaction, you have 1 mole and 1 mole for a total of 2 moles. Good? Meaning 1 mole of carbon dioxide, 1 mole of hydrogen. There's 2 moles on that side, aren't there? What about the other side? 2 moles. So which side is smaller, the reactants or the products? Is the side with 2 smaller or the side with 2? They're equal. So in this reaction, there would be no change because the 2 sides are currently equal. Usually, when the volume decreases, it goes to the smaller side. But since neither side is smaller, it doesn't change. So let's change the question. I'm going to pick a new color to write in. Ooh, let's go red. If this question had been slightly different, let's say that this was a solid. We don't usually count solids, right? Remember up here? Solids get replaced with the number 1. So we don't worry about the solids. How many gases are on this side? 2. How many gases are on this side? Only 1. So if this question had been different, if it had been 2 gases and 1 gas and a solid, it would have gone to the right. So you do have to pay attention to the states of matter. The reason for that is, and I think I did this last time with a water bottle, that the water doesn't get compressed, but the gas inside the water bottle gets compressed. And solids and liquids aren't impacted by these pressure and volume changes, but gases really, really are. All right, number 13. Answer the following questions. Is this reaction exothermic or endothermic? We start high and we finish low. Exothermic, energy is exiting. But Mr. Murphy, aren't we putting energy in? Sure we are, but we get that energy back and we get a whole lot more, don't we? So with exothermic, you end up losing energy through the process. Let me just add some graduation marks here. 0, 2, 4, 6, 8. Who do we appreciate? All right. So you can see that based off of this amazing scale I just created, it starts at 10, it finishes at 2, so it's losing 8. You could even go, it starts at 10, it goes up to 14, back to 10, so you put in 4 and get the 4 back, and then there's an additional 8 released. If you're talking about this is the energy of the reaction. That would be a comparison of letter C to letter D, where you start at 10 and you finish at 2, you're releasing energy. Which of those letters represents the activation energy? Yes, going from C to A. Once you hit A, you've reached the activation energy, and this reaction will react. And then this one here, the catalyzed pathway, is a lower pathway. We're going to take a look at catalysts and demonstration-wise in a minute also. Works pretty well. Okay, cool. Test next class. How do you study for a test? Start with the review sheet. You do the review sheet. Then you go through the notes. You look through the notes and you go, well, I don't remember that term or this term. Make sure you review everything in the notes. And just be sure you know everything. If you know everything, you can't fail. Unless you pick the wrong answers for everything. That would be horrible. Okay, one last thing that's really important. Make sure you don't